So now that we've discussed angular acceleration of objects that are rotating, let's revisit a topic from Unit 2, namely pulley systems. So we have our good old familiar Atwood machine. We have a block with mass m1 greater than m2, so that we know that m1 is accelerating down, m2 is accelerating up. But what we're going to change now is we're also going to consider our pulley, which will have mass m3, as well as moment of inertia, 1/2 m3 r squared. And so what we're going to change now is we're going to consider as well the angular acceleration of our pulley. In the past, we assumed our pulley was massless, and we assumed that our rope sort of slid over the pulley. What we're now going to do is drop that assumption. Instead, the pulley will be angularly accelerating and doling out the string such that the string does not slide over the pulley. To avoid that, what that means is that we have a relationship between A and alpha, namely A equals R alpha, and this will be such that the tangential speed of the pulley will match, or the tangential acceleration of the pulley will match the tangential speed and acceleration of the string. With that, what we can immediately see is that the tension in the string will no longer be constant. And so with that, let's begin to try to find the acceleration of the system. And one thing that hasn't changed is that we can do free body diagrams for M1 and M2. So for M1, we've got tension. Instead of labeling it generic tension, I'm labeling it T1, since we know the tension will vary on the two sides. We've got M1G. And then for M2, we have T2 and M2G. And with that, we can write our F equals ma equations. For M1, we'll have M1G minus T1 equals M1A. And for M2, we will have T2 minus M2G equals M2A. And what we'll notice, of course, is that these are two equations in three unknowns, which means it's insufficient to solve the problem. So what do we do next? Well, we've neglected part of the physics of the problem. We haven't looked at our pulley. Well, our pulley is not translating, so no need for F equals ma, but let's consider torque equals I alpha. So what forces act on our pulley? Well, we have T1 pulling down on this side. We have T2, which is lesser, pulling down on that side. We, of course, have mg. And presumably we also have some sort of support force at the pulley pin, which I'll call F support. And if we use the pin as our reference point, what we'll notice is that F support and mg exert no torque because they act at the reference point. Instead, we have T1, which acts at a distance r from our reference point at an angle of 90 degrees. So that will produce a torque T1r in the direction of our angular acceleration. That's why I've chosen to make it positive. And then we will have T2r against our angular acceleration, and this will equal I alpha, or 1/2 m3 r squared alpha. All right. And so now we have a third equation, but we've added another unknown, namely alpha, except, of course, recall that A equals R alpha, and therefore we can replace one factor of R as well as R alpha with just A. And so now let's put all of this together. We can cancel out that last factor of R, leaving us now with a nice system of three equations in three unknowns with our usual beautiful dynamics property, namely T1 positive here, negative here, T2 negative here, positive here. We can add our equations. And so this gives us M1G minus M2G is equal to M1 plus M2 plus 1/2 M3 times A. So that our acceleration is equal to M1 minus M2 over M1 plus M2 plus M3 over 2 times G. Now, What you may be thinking is there a system approach that we can use here, just as we had in linear dynamics? And the answer is yes. What you may notice is that our upper term, m1g minus m2g, matches what we expect the external force on the system to be. So F external is equal to m1g minus m2g. The only change we have is when we consider the mass of the system. As before, we have the mass of our two blocks, m1 plus m2. But what about the mass of the pulley? You'll notice we have m3 over 2, not m3. What we have instead is what I will call the rotational mass of our pulley. And our rotational mass is our moment of inertia divided by r squared. In this case, m3 over 2. And understanding the notion of rotational mass will be quite important down the line as a shortcut. And so we will definitely discuss this in upcoming videos.